Hello everyone and welcome to this first video in our comprehensive series of videos about chip packaging. Today we'll be talking about traditional packaging technology. My name is Alonso and I'll be taking you along through this journey. So to start with, we're going to go through the history of packaging. First packages they came up with, they used pin-through-hole technology. So pin-through-hole technology is pretty self-explanatory. The pins would be inserted into a socket or soldered through the hole in the PCB. And there's three main types. There's DIP, dual inline packaging. There is SIP, single inline packaging, and there is other variants like CDAP, which is a ceramic DAP instead of using plastic. And for most of these, there is a 0.1 inch pitch distance, which means the distance between the two different pins. They're spaced by 0.1 inches. So we're going into the first type of package, DAP. It was invented in 1964 at Fairchild, and it was invented by Brian Rogers. And the original design had 14 pins with 7 pins on each side. It was invented when the traditional number of leads became a problem for increased number of transistors. So obviously the demand for transistors in a smaller space increased, and they needed to come up with a solution to put them into a tighter space, and this type of packaging was the solution. Usually they have a pin count of 4 to a maximum of 64 leads. And in this case, the structure of the chip really limits the maximum number of the pins that you can have. Because obviously when the pin count goes up, then the packaging gets a lot larger, and it also has to have increased width. It also happens like this because the pins radiate from the center towards the outside, so the die will be here in the center, and then all the pins which are with a fair enough distance between them, they have to come in really close towards the center. So at some point it just gets really complicated to add more pins to that. There's also the problem that the package is a lot larger than the die itself. The die is a very small component in the center, and then the package ends up being very big. And this, like I mentioned before, limits the number of leads, and it also ends up being an inefficient use of space. The DIP also counts with a notch at the top that helps assembly not only for humans but also for machines, so they can know which direction to put it in. And it also helps us count the number the pins. So for example, with the pin with the notch located at the top left pin would be number 1, and then as we go down through that side we would have 2, 3, 4, and all the way down, and then we would start counting from the bottom up on the other side. So most DAPs are made of plastic or ceramic molds, and what they do is they create a moisture and air protection inside for the die, which helps with reliability and how long these chips can last. Then the leads are wire bonded to the silicon die, and then they usually use gold wire bonds for this. Now the bonds are not too tightly bonded to avoid breaking in case of any mechanical stress, and there's a frame that brings together all of the leads, the lead frame that stands on the periphery, and then that is connected to the die through the wire bonds. Now this type of chip fell off in use with the introduction of SMT, or surface mount technology, and is nowadays used mainly by hobbyists in things like resistor packs, switches, or LEDs. And if you've taken any electronic courses with a laboratory where you had to assemble a circuit, it's very likely you've had to use some of these DIP components. Now I would also like to mention, do a little mention to SIP, which is single inline package, which was very similar to DIP, but it only had one line of leads. And they share one common pin. So one of the pins will be common for all of them, and then from there it diverges. It can be used for different uses like resistors, but it's mainly used for memory modules. And they can have only up to 24 pins, which again, with the higher demand for transistors in a smaller space, that wasn't enough. Moving on, then they developed, since they didn't have enough space for that as many transistors and as many inputs and outputs as they needed, they had to come up with something else, and their solution was surface mount technology, or SMT. Now there's lots of different types of SMT, but we're only going to focus on a couple. The main thing about SMT is that it solders directly on top of the board. It doesn't have to go through the board. So it occupies a little bit more space. It's smaller than pin through hole, but there's also comes with it the drawback that the risk of defects increases due to component miniaturization and denser packing of boards. So the components were closer together. It's easier to have a little mistake. However, they are faster for automated assembly, and they can be soldered all at once instead of having to solder pin by pin. And then the three main types that we're going to focus on is going to be QFP or quad flat package, PGA or pin gate array, and BGA or ball gate array. Now, the QFP was the first one that was developed, and it was developed in the 60s, but it was first used commercially in the 80s. And something interesting is that NASA used this before it was actually used by the industry, and it had been used in Japan since the 70s, but over here it was in the 80s when they became much more popular. The main thing that these accomplish is that they have a much higher number of pins, ranging from 32 to 304 pins. And the pins are located also much closer to each other instead of being 0.1 inches apart, which is the standard for other types of packages. Here, the leads can be positioned much closer to each other, allowing for a higher density. And since they're directly soldered onto the top of the board, they don't necessarily need to fit any sockets, then that was fine for this type of packages. Now, the leads are very particular because they have a gold wing shaped lead on the four sides of the packet of the package instead of being only on the two sides like the LED. And the wing shape is this thing that we can see over here. If you can see, the lead comes out horizontally and then it bends backward downwards, and then it again bends horizontally, so then it can be soldered with the board. And those are very very common of this QFP package. And now there's some drawbacks, like the fact that the pins may suffer damage by handling because the pins on the quad flat package are small and very closely spaced, so it's easy for them to be damaged and deformed by poor handling. And it's also very difficult to reform them correctly to their original position, so that can be an issue. Sorry. And they also have PCB track density issues, where since the pins are located so closely, you need to have lots of different tracks that lead up to the QFP, so there can be some issues with designing the printed circuit board where the tracks may be a little bit too close to each other. So we have a few common types of QFP. Now there's many more than these, but the main types would be PQFP, which is plastic QFP, is the most commonly used, made out of plastic. But we also have CQFP, which is ceramic QFP, just like it was for the DIP. We also have other types like FQFP, which FQFP stands for fine pitched QFP. And again, like we said, the pitch is the distance between the leads. So fine QFP means that the leads are closer together and it has a higher density of pins. Then we also have the HQFP, which is heat sinked QFP, which just includes the heat sink that will prevent overheating and will keep the component cool enough to run. And we also have LQFP, which is low profile QFP, which overall has a thinner body of the IC instead of being so tall. This type of QFPs are widely used for ICs nowadays, and we can see in this picture on the right how there's a bunch of QFPs over here in this printed circuit board. And if you take a look at any printed circuit board, they're very common. You will most likely see a couple of those appear here and there for ICs mainly. However, eventually they fell off. They became less popular for the higher density PGA and BGA, which we'll talk about later. And the QFP simply could not keep up with the increasing demand for pins in a smaller space. So it just gave way to chips that were based on gate arrays. And this is the key term that we're going to see now. And we're going to start with PGA, which is pin gate array. Now, the plastic pin gate array was developed by Intel in 1993, but the ceramic pin gate array had already been under development way prior. And they came up with this to alleviate potential performance limiting package problems that the QFP could face. They also needed transition from 16 to 32 bits, and this was the response because pin grid array was preferred for processors with large width data buses, since it could handle the required number of connections way better than the QFP or previous models could. Um, Now the main characteristic is that it has the pins on the surface of the chip arranged in an array instead of being throughout the perimeter on the side. So it offers a much higher density. The pins are distanced in zero point 0.1 inches, just like it was in the DAP. And then sometimes they can be inserted into sockets, but they can also be soldered through the board. However, and of course, then the number of pins outnumbers any previous technology that we had seen before by far. It just adds a lot of new possibilities for things you can do with these. Some of the drawbacks are that they can be more fragile and unreliable. And PGA is cheaper than other grid arrays that we'll see later, but the pin connections of the PGA are often less reliable, and the PGA technology also had some limitations on thermal and electrical capabilities. So they're still used, but usually they're not as reliable as others can be, even if they're cheaper. And they fell off popularity because they're a little bit fragile, and BGA or Ball Grid Array, which we'll talk about in a second, they just took over. We have several types of PGA. We have plastic PGA, which is just a PGA in a plastic packaging. We have the ceramic PGA, which is in a ceramic packaging, and you guys can see a trend here. Then we have a very interesting type of technology here, which is not only it's not exclusive to PGA, which is the flip chip. And the flip chip basically consists on having the die facing downwards on the top of the substrate. So you won't necessarily need a plastic covering. You will just see the substrate directly, and then the die will be hanging from it, and it would connect with micro bumps, soldered micro bumps to the die. I mean, the die would be connected through micro bumps to the leads instead of having to use wire bonds, and this greatly increases the reliability and the speeds that you can get with this instead of having to use wire bonds. We also have a staggered PGA where the pin layout is positioned in diagonally, in kind of like a diamond shaped, instead of having just be rows and columns, so you can have more pins per unit space. And another common type is the organic PGA, where the die is just attached to an organic plastic plate instead of your usual one. And this type of chips are usually used for computer chips. And then as an example, we have the Intel's Pentium 3 microprocessor, which we can see on the picture here on the right. And then you wouldn't be able to see it from this side, but on the other side, it just has a bunch of pins hanging out from there. So, like we said, the PGA had some reliability issues, and a way to fix that would be the BGA, or Ball Grid Array. So Motorola and Citizen jointly developed the plastic BGA in 1989, but the widespread use of the BGA was seen in the mid-90s by companies like Compaq Computers or Motorola. And BGA appeared as another solution to the I/O limitations of QFPs. So, for example, the BGA can have up to 1,000 bumps in every chip, but usually it ranges from 50 to 500. But compare that to the 304 maximum that you could have in a QFP, and these are also a much smaller area. So, just for comparison, a QFP would have 232 leads in a 40 by 40 millimeter body, while a 27 times 27 millimeter body on a BGA can house up to 225 IOs. And the solder balls would be spread further apart than the pins would be on a QFP. So it makes it easier to solder, less cramming per se, but you can still get a much higher number of solder balls than you would get with the leads in a QFP. And the good thing about having the inputs on the surface instead of on the perimeter is that as you increase the surface, the number of pins increases quadratically to a power of 2 instead of only increasing linearly with the perimeter like the QFP would do. So some of these were the reasons why this type of designs became much more popular than the QFP did for some of these chips. So the main difference between PGA and BGA is that these technology uses solder balls instead of the pins. So by using the solder ball, it has a couple things come with using the solder ball. So the first thing is that it's permanently mounted to the IC. The IC is permanently mounted to the board. You can no longer just use a socket to extract it easier, and trying to desolder this is very complicated. So usually when you solder it stays there permanently. They're also thinner than the PGA because it doesn't need the length of the pin, obviously. But then you also don't have the sockets available for this kind of technology. Now, they provide higher performance, higher speeds, and more resilience. And this is due to a couple factors. First of all, the leads are much shorter, which leads to higher performance and higher speeds. And then they also have a high heat conduction and higher thermal resistance, so the heat flows more easily to the PCB, preventing overheating. And then the leads have a lower inductance because the shorter the conductor is, the lower the unwanted inductance. And some unwanted inductance can create interference with the signals that are going through the leads. So all of those are, very good factors from the BGA. However, some of the drawbacks are that they can be less reliable in extreme conditions, and the bigger one is that they're more difficult to inspect. So, for example, in extreme conditions like extremely high temperature, high thermal shock, and high gravitational force environments, the BGA can be less reliable due to lower ductility. And then mechanical stresses can be overcome by bonding the device to the PCB using an underfill. So that's a way to solve this problem. Now, the biggest thing is that it's very difficult to find the soldering faults. In order to do this, you would usually need to use the technology of X-rays or things like microscopes, or there's technologies that have been developed to look specifically underneath the package. And since X-ray is very expensive, usually what they do is they're diagnosed with using an electrical test, but it's really hard to actually inspect the chip. BGAs are very widely used today. They're, for example, used by iPhone or a lot of computer chips. It's usually the preferred type of connection for the chips nowadays. So we have a few types of BGAs. As always, we have PBGA, plastic BGA, and CBGA, ceramic BGA, where the ceramic offers a little bit more reliability. But also, we have some interesting ones like TBGA, which is tape or tab BGA. So these are based on a flexible film or tape, which is covered with copper metallization on both sides. So these have improved electrical and thermal performance over over your standard PBGA. And then the SBGA or Super BGA is, it has improved electrical and thermal performance over the PBGA as well. And it uses a metal heatsink plate attached to the backside of the chip, which provides power dissipation, as well as it serves as a stiffener and ground plate. In this one, unlike the tape BGA, the chip is generally wire bonded instead of using microbumps. Now, the BGAs are used for plenty of purposes. Some of them being microcontrollers or microprocessors. They're used for telecommunication devices. They're used for like RAM memory chips, or for like any other kind of PC chips. And just as an example, we have that the micro FC BGA, which FC stands for flip chip, which is what we talked about earlier with the PGA. The micro FC BGA is Intel's mounting method for mobile processors, and it was introduced with their Coppermine mobile seller, and we can see an example of that in the picture over here, where this is one of the Intel's processors. We can see how the BGA is used in the back, like that. A lot of the times you will find that the center part of the chip is has a little empty square. It's not always the case, but you will see that often. And this BGA technology really is what's mostly used for computer chips and things like that. So anyway, just to recap a little bit, we have the chips that have been evolving through the years, and we have a little bit of a chart here to give us some guidance. So first we had the pin through hole with the DIP, which was very most popular in the 70s. And we saw that there's other technologies like the SAP, even if they're much less popular. And then they developed the surface mount technology, which mounts the pin directly onto the board. And we started with the QFP midway through the 70s. It increased a lot the IOs. It was a great opportunity for higher increased number of transistors and number of pins per surface area. And it's widely used for ICs and PCBs. But then as we moved over towards the 80s, computers mainly needed a higher bit rate, and they needed higher numbers of IOs per unit area. So then engineers developed the grid arrays, starting with the PGA in the 80s. And the PGA has the pins that can be put into sockets, or they can also be soldered. And it's a little bit more fragile than the BGA, but it's also cheaper to produce. And then finally, as we get more closer to the 90s, we get the BGA, or ball grid array. And this is your standard practice for a lot of computer chips. It's used in things like iPhones. It's been used for Intel mobile processors, you name it. So yeah, that would end our presentation for traditional types of packaging. I hope it gave you a wider understanding of how the packaging industry has been evolving, and why, which is mainly driven by, at first at least, it was mainly driven by being able to increase the number of pins per chip, and having to have it do it in a smaller area, and that's how we get all the way to the BGAs in the 90s. So anyway, I hope you enjoyed the video. That's it for today. Please stay tuned for the following video where we will talk further about chips. Bye bye.